Greetings, comrades. My name is Gigantals, and welcome to episode 2 of our Global Warming Will End the World, or my Global Warming lecture. So, last episode we covered the role of the carbon cycle in this. In this episode, we're going to be looking at the chronology, the timeline of global warming and global cooling. Anyway, so this episode, we're going to cover what is global warming, why were there the ice ages, and when's the next ice age, which should be quite interesting. And this episode is going to be quite long because there's a lot to cover. So you may want to pause the video, grab a drink and some food, because this is going to be a proper lecture. Okay. So, what is global cooling? Global cooling is the gradual or sudden decrease in global temperatures. This can be due to large glacial advances. Large amounts of particulates in the atmosphere reflect significant amounts of infrared radiation away from the Earth's surface, lowering global temperatures. So that's like it's like having a mirror up in space that reflects all the sun away, or the light from the sun away. The number of sunspots recorded on the Earth reaches almost zero, the gradual cooling of the Earth due to the Milankovitch cycle. And there are other reasons, we'll explore them later. So, the global cooling led to, on several occasions, the whole planet just froze over, snowball Earth. Global cooling is also more likely to happen than global warming in terms of timescales, and until the Industrial Revolution, global cooling would have been more noticeable. So the ice ages, before we get onto the actual ice ages, let's start the case study. So the reason I'm going to start the case study is because the ice ages happened thousands of years ago, and there's not too much evidence about it. What I'm going to look at is it has a lot of evidence behind it, and we can use it on a bigger scale so we can understand how the ice ages thousands of years ago happened. So the case study is the period of time known as the Little Ice Age, which was
1300
to 1850. The global temperatures dropped, and there were a bunch of reasons. It includes the decrease in sunspot activity, the 1275 eruption of the Summerlast volcano, the 1250 Atlantic pack ice expansion, and oceanic circulation, and the Milankovitch cycle. And in the background, you've got a little picture of one of the frost fairs that they used to have on the Thames during winter, where the whole Thames would freeze over and it would be strong enough that people could walk. In fact, it was recorded that elephants could walk on the ice, it was so thick. So, first of all, sunspot
activity.
Sunspots are small, cool areas of the sun that appear black in color. They look tiny, but they can be much bigger than the Earth, and they have a direct impact on our climate and the sun's magnetic field. From 1460 to 1550 and 1645 to 1715, there were two periods of time where the amounts of sunspots recorded were extremely low, in the Sporo minimum and Maunder minimum. Sorry if I'm pronouncing it wrong, but as you can see over here, with the mouse, as you can see, low periods of activity, and this is important because the amount of sunspots were low, and this helped maintain low temperature levels across the globe. And the reason why sunspots activity is so important is because the less sunspots there are on the sun, the colder it gets here on Earth. We don't understand it too much because sunspot activity has only been observed and recorded for 400 years. Because before then, if you looked up at the sun, you'll be blinded for a few minutes. And it's only recently we've actually managed to look at our prop telescopes and see these sunspots. So the sunspot cycle it's incomplete as far as we know it, but the 11 years could be a fraction of what it could actually be. I mean, it could be thousands of years long, and it could help explain previous ice ages, but sunspot activity is still a relatively new theory, and we're investigating it. So the next one is volcanic eruptions. There was a period of heightened volcanic activity during the Little Ice Ages. Other than pumping out carbon dioxide, volcanoes also produce ash and carbon particulates that can rise and remain in the atmosphere for many years. So it acts like a blanket around the Earth. And sulfur dioxide, also produced, would react in the upper atmosphere and form sulfuric acid crystals in the clouds, reflecting more heat away. The larger the eruption, the more particulates produced, which then in turn lowers the temperatures more. There was a similar eruption happening in 1257 on the island of Lombok, Indonesia. It was a VEI 7, which means that it was huge. It's one step short of VEI 8, and the higher the number, the more cataclysmic the effects are. VEI 7 means it's affecting the whole planet. And while this eruption was one of the biggest that has happened, since Homo sapiens walked the Earth. Ash was throwing tens of kilometers high into the atmosphere, and ice cores from the poles confirm that this strengthened the glacial advance that had only started 7 years previously. And they know this because when they go drilling for the ice cores, they find layers of ash which date back to this time period. But there's even more. Not only did the Summerless volcano erupt, but during this ice ages, there were 6 recorded eruptions that reached VEI 6 and 1 that reached VEI 5. In total, they produced 306 cubic kilometers of tephra, which is rock, ash, and gas. This is a huge amount. If you think about 306 cubic kilometers, that's a large amount of tephra produced, and that would have increased. That would have improved. That would have just strengthened the volcanic blanket around Earth. So the volcanoes that erupted were the Kauai caldera, which we don't know the strength of it or the year it erupted, but it was around this period. Mount Tarawera, 1310 to 1322, so it was quite a long eruption, VI 5. Long Island, 1660 to 1680, 20 years eruption, VEI 6. Colombo, 1650, VEI 6. This one's in the Mediterranean. Ardabunga, 1477, VEI 6. I hope I pronounced that right. Kilotoa, 1280, VEI 6, which is in South America. Huaynaputina, 1600, VEI 6, again in South America. And Billy Mitchell, 1580 to 1600, VEI 6. As you can see, these all, if you look at from Long Island, Colombo, Huaynaputina, and Billy Mitchell, you'll see that these all happen quite close to each other. That is important. That would have just increased volcanic debris in the atmosphere that was already there. So, next, the Milankovitch cycles. So, there are 3 factors that the Milankovitch cycle depends on. The eccentricity, or the shape of the Earth's orbit, the axial tilt, between 21.1 and 24.5 degrees, and the precision, the axis wobbles, how the axis wobbles. Depending on the Earth's position, the critical molecule in the atmosphere, carbon dioxide, will vary in concentration. Now, the Earth's orbit isn't circular, it's elliptical, which means that in certain points in the year, it's closer to the sun than it is on other points of the year, which is quite far away. As you can see by the diagram up here. Different periods of the year, it's further away, it's closer. And this is the reason why it's elliptical. This isn't even. This is just 1 year, because the eccentricity of the orbit can change. And this is because there are strong gravity from planets out there like Jupiter and Saturn, poke and pull on the Earth, change the shape of its orbit. Each cycle lasts around 100,000 years, and if the northern hemisphere is further away from the sun for longer periods of time, the land masses will cool and glaciers will advance. Carbon dioxide will be stored in the ice waiting to be released. The axial tilt. Again, it varies between 22.1 to 24.5 degrees. We're currently at 23.5 degrees, and the reason why this tilt changes is ever since the Theia, the protoplanet, the size of Mars that hit us, created the moon, but ever since then we've been on a tilt, and we're still shaking from that collision. We're moving back and forth really slowly. It takes 41,000 years to change between 22.1 to 24.5 degrees and back. And again, this is important. If the northern hemisphere is tilted away from the sun for longer periods of time, the land masses will cool and glaciers will advance, and carbon dioxide will be stored in the ice waiting to be released. Next is precision. The axis wobbles as it changes from 22.1 to 24.5 degrees, which means that although it's moving in a constant direction, that's its net movement. Otherwise, it's moving back and forth constantly. So it's like you leaning forwards and backwards really fast, but you're still walking forwards. These are caused by tidal forces influenced by the sun and moon. The Earth isn't spherical and is slightly bulged around the equator due to the Earth's spin. This, combined with the tidal forces, leads to the axis wobbling slightly. Each wobble cycle lasts for around 26,000 years, and this combined axial tilt can lead to longer periods of the northern hemisphere seeing the sun less, cooling land masses and causing glacial expansion. Carbon dioxide will be stored in the ice waiting to be released. You can imagine how that is now. The point about this is that the longer away the northern hemisphere away from the sun, the colder it is, causing glacial advance. Next up is the
1250 pack ice expansion,
which basically means that during 1250 there were reports from Nordic colonies in Greenland and up north in Iceland that stated that the pack ice in the Arctic Ocean had started to increase south. Pack ice is, when you go to watch like Blue Planet or whatever, and frozen planet. You know when you see all the ice on the ocean? That's pack ice. And what they're saying is that the sea started freezing further south. The Norse also reported that the Greenland glacier grew in size and became a threat to their colonies there. This is important because this would mean more carbon dioxide is being trapped in the ice, and during the 1257 Samlas eruption, which was one of the most significant eruptions in that time period, it would have strengthened.
Pack ice expansion.
And it would have kept on expanding south and cooling the planet. This more or less stopped at around the Industrial Revolution, and this released carbon dioxide back into the atmosphere. Next one, oceanic circulation. I was going to include a picture of the movie Day After Tomorrow, but due to copyright reasons, I can't. But the logic of the movie is that out of all the water on Earth, 3% is fresh water and drinkable. 68% of this fresh water is locked in glaciers and ice caps. But because global warming is melting those stores of fresh water, they enter the ocean. This interrupts the fragile current in the
Atlantic
Ocean that brings warm water north and cold water south. All the fresh water is messing up with this current, and this is starting to change weather patterns, and eventually to lead to a new ice age. And this is actually true, although
heavily exaggerated.
It was the cause of the Little Ice Age. You see, before the Earth started cooling down in the Little Ice Ages, there's a period of time known as the medieval warm period, 950 to 1250 AD. This is when the Earth was particularly warm. It was around the same level as 20th century temperatures. Because of this warm period, the polar ice caps would have been melting, releasing fresh water into the ocean. Not only that, but also glaciers up on the mountains and all the tundra up north. Carbon dioxide would also be released in the ice, and this in turn would lead to weather changes across the globe, be warmer. And so the thermohaline current is the name of the global oceanic currents. As you can see, warm water is carried along up here. This is the reason why it's not so cold in Britain or Canada freezes its ass off in winter. It's because of this warm current, all taken down south. Warm water floats, cold water sinks. So that's why they can cross over. So as you can see, cold water is brought up north around the equator where it warms up, and then it flows back south and completes the circle around the world. So in the movie, the thermohaline current was affected, and the northern hemisphere suffered major temperature drops that froze people instantly. In reality, this would have been a slower process because you can't freeze instantly. That's just not right. Because we're still warm. Yeah, the movie had a bit of a problem. Also in the movie, the East Coast has a massive storm surge that was the equivalent to a tsunami. In the movie, they were actually mentioned it. They thought there was a tsunami coming from up north. The huge quantities of water from the melting polar ice caps can cause a huge wave. They would be a bit more slower because there's nothing that would work that fast. Meanwhile, in the southern hemisphere, the storms would increase in intensity. The recent climate phenomenon, El Nino and La Nina, which is how you pronounce them, will also increase in intensity and cause more havoc in the Pacific. Because that's where they're affecting changing warm and cold air currents, precipitation, no precipitation. You're messing stuff up. So oceanic currents are important. They dictate the weather of the planet, and that's why they're important. They did help bring about the Little Ice Age, and we haven't studied them long enough to know there's a cycle that they go through. But we can assume that 950 and 1250, it's more or less the cycle starting over again sometime in the 20th century. But they're still fragile and susceptible to change. So what does the Little Ice Age have to do with the Ice Ages? Yeah, let me show you why. The Little Ice Age was the beginning of the next Ice Age. Dum dum dum. So now we're going to expand on the connection between the Little Ice Age and the Ice Ages. So the Ice Ages were periods of time where global temperatures dropped, glaciers expanded, and the ice caps grew. They were basically much bigger versions of the Ice Age and lasted for thousands of years. The causes of them, again, as we explored earlier, were decreased sunspot activity, volcanic eruptions, oceanic pack ice expansion, oceanic circulation, and the Milankovitch cycle. There are two more that I'm going to go into detail because although they didn't happen in the Little Ice Age, it did happen a lot in the Ice Ages. So we've got the supervolcanic eruptions and the Caledonian cycle. Supervolcanic eruptions are caused by supervolcanoes, obviously. Supervolcanoes are freaking huge volcanoes. They can cover many kilometers in area. They are that big. They cause VI 7 to 8 level eruptions, affecting the whole planet. And just talk about how big they are. Some volcanoes, when they erupt, they produce several cubic kilometers of tephra. Supervolcanoes can produce thousands of cubic kilometers of tephra. They inject ash and other particulates several kilometers into the atmosphere. In fact, there was an article a few years ago about how a volcano apparently punched a hole through a cloud with a shockwave. This would decimate the entire weather system of a country, if not a continent. And one supervolcanic eruption will create a global winter that will last for several years, global cooling, because of all the particulates put up into the atmosphere. The only scenario that could be worse, that could match this, is a nuclear winter following a nuclear war. Supervolcanoes are the most damaging natural disaster on the planet. The only thing that can beat them, that isn't man-made, is an extraterrestrial impact. Only a meteor could cause more damage than a supervolcanic eruption. That's how big they are.
Let's just go.
And talk about how much tephra is produced, just to show how big they are. So here we got, you may remember Pinatubo, 1991, VI5, 5 cubic kilometers produced. Okay, quite big, level pyroclastic flows. Krakatoa, 1883, VI6, 20 cubic kilometers. Decimated the island of Java with pyroclastic flows and a tsunami. Great Lake, 7,600 years ago, VI7, 150 cubic kilometers. Yeah, okay, big enough. But this was a small supervolcanic eruption. Long Valley, slightly bigger, 76,000 years ago, VI7, 580 cubic kilometers. That's a lot of tephra. One of the many supervolcanoes in the US. Yellowstone, 640,000 years ago, VI8, 1,000 cubic kilometers. That is a lot. That's the last eruption of Yellowstone. Then you have Toba, 74,000 years ago, VI8, 2,800 cubic kilometers. Almost 3 times as much as Yellowstone. There's a difference between. According to evidence recorded from the following tsunamis and earthquakes produced, the population of Homo sapiens was driven down to 10,000 individuals globally. That's right, Toba almost wiped us out. Then we have the Wawa Spring, 30 million years ago, VI8, more than 5,500 cubic kilometers. The Wawa Springs, they were a supervolcano that we didn't know about. We only learned about it recently. But as you can see, it's also in the US. It's much bigger than Yellowstone.
Barana and Etendeka traps.
132 million years ago, VI8, more than 8,600 cubic kilometers. The largest explosive eruption ever. You may want to know explosive, effusive. Explosive is
Krakatoa.
Big explosion. Effusive is explosions, but multiple small explosions, gentle stuff, not as violent. This one happened in South America, as far as I remember. Then we had the Deccan Traps, 64 million years ago, VI8, more than 9,300 cubic kilometers produced. Largest effusive eruption ever. Yeah, the date may be familiar. The Deccan Traps eruption helped kill out the dinosaurs. Yeah. And now we have onto the big
Mother Nacho.
The Siberian Traps eruption, 250 million years ago, VI8, more than 4 million cubic kilometers produced. The largest eruption in the history of planet Earth. 250 million years ago. According to evidence, was the Permian-Triassic mass extinction. 96% of all life on the planet died. Yes, the Siberian Traps almost wiped out all life on the planet. That's how freaking big it is. And as you can see, these two pathetic things are nothing compared to that. But we haven't had a supervolcanic eruption that big for a while. Let's focus on stuff that we're going to be more concerned about lately. So let's focus on Yellowstone. Yellowstone and Long Valley. Because the soon-to-be supervolcanic eruptions will be around the size of the Yellowstone and Long Valley. So let's compare. Yep, supervolcano is going to do a lot more damage. Anyway. Although releasing carbon dioxide would increase global temperatures, the immediate effect of a supervolcanic eruption would be the ash and tephra blocking out the sun and lowering temperatures within hours. Volcanic ash spreads very quickly once it gets into the wind currents. In the jet stream, within a day, it's covered from parts of Europe to most of Europe and huge sections of Russia. It's possible that after the global winter, that the carbon dioxide produced during the eruption will take effect and slowly warm up the planet. Global warming. But because no supervolcano has ever erupted in recorded human history, we don't know what the full consequences of a large eruption would be. However, it'd be one of the greatest freaking sights on Earth. I want to be in the best seats in the house, but also have a good chance of surviving. Because I love volcanoes. I want to see what a supervolcanic eruption looks like. You ever hear, if Yellowstone's erupting, I'll probably be there watching somewhere. So let's explore. Why am I showing all this? So here's the timeline. Each orange line shows the eruption of a supervolcano, and each blue block shows a period of glaciation, or an ice age. During this ice age over here, Long Valley erupted, and we can see there's a little peak in global temperatures before it carried on with the ice age. Yellowstone erupted, took a little while before the planet started warming up. Lava Creek, the planet started warming up a little bit, and then, nothing happened here, nothing happened here, nothing happened here, apparently. Wakamaru, okay, planet warmed up a little bit, it's getting a bit cold, warmed up a bit there. Mount Aso, planet cooled down a little bit there. Mataina Ignim, right? Apparently there are two eruptions shortly after, as you can see, global temperatures dropped and dropped. Reporoa caldera, the temperatures dropped, eventually spiked. Toba, obvious decline temperatures. As you can see, the amount of temperatures that are recorded, we have more readings for them. That's because it's a recent, it's easier to record. Campi Flegrei, temperatures dropped. Orua Nui, temperatures rose. But from the results, we can see that after each eruption, there's either a small dip in temperatures or signals the beginning of a long set of low
Temperatures.
Some of them, not exactly, so let's focus on the ones that did. Supervolcanic eruptions can't be the sole cause of ice ages, though, because between 340,000 years and 640,000 years, there's no major eruption recorded or found trace of, as you can see between here. So that means that there are other factors that helped, but supervolcanoes are still a major factor, and for all we know, they could have been the final straw on that broke the camel's back. And one thing we can confirm, however, is that global supervolcanic temperatures have a large impact on global temperatures. And the effects can still be seen a millennia later. But do you want to know about this? Well, you remember the photo, I can't do copyright reason, but the painting someone made of the person on the bridge who's like screaming and their face is all contorted. The reason why the sky is red is because that was Krakatoa. Yeah, and that was painted long after Krakatoa erupted. In fact, the ash released from Krakatoa still caused incredible red sunsets well into the 20th century. That's how long the ash stays up in the atmosphere for.
So the Cardonian cycle was named after one of RW's relatives from 100 years ago or so. He was a big fan of hers, and I named it myself because I'm the public face of Gigantals, the channel. But I decided, he's a Norse work, he's done all the stuff, he came up with the theory and everything, that I'm going to name it after him. Well, I'm going to name the cycle he created after his hero. And here we are. Yeah, so anyway.
This cycle involves plant photosynthesis, respiration, and decay over thousands of years, and it covers both global warming and global cooling. And yes, I came up with this cycle myself, and there may be a few little errors with it, but this mainly does explain what happens to the plant life on the planet during and outside of the Ice Age periods. Most of the world's land masses are in the northern hemisphere, as you can see with the equator over here. This means that during the summer, a lot of plants grow all at once, and the carbon dioxide level in the atmosphere visibly goes down, cooling the planet. During the winter, as all plants die, a lot of carbon dioxide is released all at once, which increases the temperature in the atmosphere, warming the planet. That's why in charts like I'm going to show you in the next slide, the temperature throughout the year spikes and drops suddenly, as if the planet were breathing, which is kind of cool. But the next change in temperature is shown at the trend of the graph. So as we can see here, there's a big thing between them. Every year has two of these dots, the highest one being summer, lowest one being winter. If not, that'd be slightly concerning. But it's evident to say that it's almost as if the planet really does breathe. But lately there's been a positive trend in which global temperatures are rising. And although this is showing the world temperature of the ocean, that's important because, like I said, the ocean dictates the temperature of the whole planet. So if the ocean starts warming up, the weather's going to change. So, part 1 of the cycle. So the cycle begins with a lot of plant life photosynthesizing.
This takes place before the age of humans, so
there's no deforestation or anything. So as they photosynthesize, because no carbon dioxide is entering through the atmosphere at a rate which photosynthesis can't handle, the average amount of carbon dioxide in the atmosphere decreases steadily. So they're photosynthesizing more, so the output is more than input. After thousands of years, the amount of carbon dioxide in the atmosphere is so low that during the winter, glaciers expand and tundra stretches further south. This kills most of the plant life, and instead of them decaying immediately, they are frozen and preserved. And this can take several decades for it to expand south enough. Just important information. The forests that are frozen are usually the coniferous forests up north. The coniferous forests actually photosynthesize faster than the deciduous forests down south, which mainly like the Amazon or the Congo or the rainforest down south. Meanwhile, the great forests of the north, of Canada and Russia and Europe, those ones are getting frozen. And the coniferous forests actually photosynthesize more than the deciduous forests. If you lose the coniferous forest, it's equivalent to losing more than a lung. But the main deciduous forests are further south, which are safe from the expanding tundra and glaciers. So although the temperatures drop slightly because they're near the equator, they stay warm. The temperature and carbon dioxide levels will constantly fluctuate as deciduous plants photosynthesize, respire, and decay. Going back to this slide, but the levels would fluctuate more. There's not much coniferous forests photosynthesizing year-round to maintain the base level of photosynthesis. And so the deciduous forests keep on photosynthesizing. However, without the cousins up north doing most of the work, they're slowly overwhelmed by the processes, volcanic eruptions, small extinctions due to the advancement of the glaciers. Species that are stuck on islands that can't move, they die. And this adds carbon dioxide into the atmosphere. It was hard to find any other color that would show out against this with all the other colors in the background. Anyway, so carbon dioxide levels slowly start to increase, which warm up the planet. This means that tundra that advanced south starts melting. Plant animal life that was frozen and preserved now starts to rapidly decay. This releases more carbon dioxide into the atmosphere, so more ice melts and more organic matter melts and so on in a positive feedback loop. The ground after the tundra and ice retreats, especially after the organic matter decays, is left as exposed dark soil and rock because it's dead. This heats up the planet by absorbing infrared radiation, because white reflects, black absorbs. The more plants grow in the barren landscapes, they start to photosynthesize more. However, the rate of carbon dioxide entering the atmosphere reaches the point where it is so high that the photosynthesis is struggling to keep up, which is known as a runaway effect. The planet gets so warm that enough plants are growing, and the coniferous forests of the north have recovered fully. The temperature increase slows down due to the amount of photosynthesis going on. The temperature and carbon dioxide levels peak, and from then on slowly decrease, leading to the beginning of the Caledonian cycle again. And here's an example of how it works. The photosynthesis overtakes the carbon dioxide atmospheric input, which leads to global cooling. Glaciers of the tundra expand, which means that the temperatures in the Antarctic are reaching below minus 10 degrees Celsius, and levels start fluctuating constantly as deciduous plants keep photosynthesizing, but the ice keeps on expanding south, and it's a bit rough to say, but they're slowly overwhelmed. Eventually, the rate of temperature of drop decreases as the rate of carbon dioxide in the atmosphere is affected by other reasons. Eventually, the ice starts retreating as the planet starts warming up. The runaway effect is eventually reached by the amount of carbon dioxide entering the atmosphere. The planet warms up very quickly. The temperatures peak, and it's the end of the cycle. So there will never be a perfect fit for the cycle on a geological timescale, and it's mainly because it's a very fragile cycle, and it's influenced a lot by other factors such as supervolcanic eruptions and long winters. But it is important because it gives you an idea of what the plant life was like, and it does give you an idea of how photosynthesis helps affect the global temperatures and levels of carbon dioxide in the atmosphere. All these factors lead to the ice ages. Carbon dioxide in the atmosphere is a critical factor that determines if there's an ice age or not, obviously enough. We've seen this through all of the cycles, and as you can see here, every time there's a peak in the carbon dioxide concentrations in the atmosphere, the temperatures in Antarctica increase. You can see that.
Oh yeah, this is the part that RW had to change recently, because he found out that this next factor was a major cause of ice ages, and so you had to quickly get a bunch of information down quickly and start putting it together in the presentation. So this is still quite fresh in terms of science.
So continental drift is quite important. You may not think of it because it's so slow or because it's related to geology, but it's very important. And here's why. You remember how I said before that most of the land masses are in the north, and when winter falls, CO2 levels rise because of all the plants dying in the south? That's because of continental drift. And so this is why every time you tell me about the ice ages, this happened within the Quaternary ice age period of glaciation.
2.588 million years ago to present.
All the ice ages I've been talking about happened here. However, this isn't the only period of constant glaciation that we've been having. There was the Pongolan, which was 2.9 to 2.78 billion years ago. The Huronian, 2.45 to 2.1 billion years ago. The Cryogenian, 720 to 635 million years ago. Nandaean Saharan, 450 to 420 million years ago. And the Karoo, 360 to 260 million years ago. So everything, all the ice ages we've been experiencing over the past 2.5 million years, all those ice ages, they all happened for the other periods of glaciation as well. So during the Pongolan glaciation,
There wasn't much known about this
period, but it was so long ago that this was the first supercontinent. Valabara. All that's left of it is part of South Africa and Australia. Craton means an area of continental crust that hasn't been affected for the past few billion years. So it's basically like a time capsule rock. The Huronian glaciation was when the world is a collection of islands being around the equator and southern hemisphere. And I couldn't find a photo of it because it's hard to find any photos or simulations of this. But this glaciation was caused by the Great Oxygenation Crisis. So many cyanobacteria were photosynthesizing their carbon dioxide concentrations in the atmosphere dropped hugely. This caused the first snowball Earth. It was the longest glaciation period and ended only after ice prevented further photosynthesis and carbon dioxide was sent up by volcanoes erupting. The Cryogenian glaciation was made out of two periods of glaciation. The Sturtian, 720 to 680 million years ago, and almost froze the entire planet again, and the Marinoan, 650 to 635 million years BC, which was the second snowball Earth. It ended due to the thaw of permafrost at the equator. The Cryogenian glaciation, the world was currently united in Rodinia, the second largest supercontinent after Pangaea. But the land was around the equator, and this blocked the oceanic currents from reaching the equator, which is important because one of the important factors that the continental drift has on the global temperatures is whether it's building up around the equator so that it stops oceanic currents reaching the
equator, warming up.
Whether there's a landlocked ocean at the polar ice caps or if there's a whole continent that's frozen over at the polar ice cap.
GA stands for billions.
The Andean Saharan glaciation 450 to 420 million years ago. We found this out via evidence in Arabia, Africa, and South America. This glaciation led to many similar scarring on the continent, which actually helped Alfred Wegener theorize continental drift in the first place, because he noticed that there were a lot of similar glacial scarring on rock formations in South America and Africa, which he then concluded that meant South America and Africa were at once united. And this glaciation helped prove that. And so this glaciation was caused by the subduction of the Atlantic plates under the North American plate. This led to silica's weathering, which lowered the levels of carbon dioxide, even though levels of carbon dioxide in the atmosphere were 18 times higher than current levels. But the reason why they still dropped was because solar output was 4.5% weaker than levels today, which by itself would have caused an ice age. But the levels of carbon dioxide held that up, but now that they were dropped, led to the ice age. The location of the supercontinent Gondwana was located mostly at the South Pole, and this led to glaciation where winter fell. And before you say anything, this was not the one after Pangaea. Okay, there's no Laurasia on Gondwana. All this is Gondwana. Okay, now the Karoo glaciation. This glaciation lasted through the Gondwana and Pangaea supercontinents, so through this one over here and Pangaea. And this glaciation was caused by the evolution of photosynthesizing plants and landmass buildup at the South Pole. This period of time was also known as the Carboniferous, because there were, as it says here, it's the age of plants. And this is because this is when most of the planet was just covered in thick, luscious rainforests. And the buildup of continents at the South Pole and near the equator blocked warm ocean currents and led to the Ice Age. And as for today, the Quaternary glaciation, 2.588 million years BC to present. This is the Earth as we know it today. And the reason why during the last Ice Age the glaciers expanded so far is because the Arctic Ocean is landlocked and there's a continent at the South Pole, Antarctica, which is completely covered in ice. Another important factor, which is one of the reasons why if you look at maps of where the Ice Age is reached, you'll see that areas like the Andes had a large amount of glaciation, and the southern tip of Argentina, there was a lot of snow cover. And these because of the landlocked ocean up north and the frozen continent down south, this allowed glaciation to expand further when winters fell, and that helped lead to the Ice Age. So one of the reasons why the Arctic being landlocked was so important is because the good thing about water data has a very high specific heat capacity, which means that it's very good at storing heat. So when the temperatures dropped, it would have taken a longer time for the oceans to freeze over. But because the Arctic Ocean was surrounded by land, the ice could expand onto the land quicker than with the ocean, which meant that glaciers grew very quickly. So we need to look closely at this point in time, where the temperatures rose, where the temperature started rising, which symbolized the end of the last ice age. So around 10,000 years ago. If we look at both the circular areas, we'll see that in this very corner here, you'll notice that just before the scale ends, the carbon dioxide concentration decreases slightly, and so does the temperature in this little dip over here. But as you can see, it then rises up here because this is modern day. Temperatures rising and global warming, stuff like that. Yeah, both peaks for the drops are fairly recent. So this is the medieval warm period over here, and then just as the temperatures and carbon dioxide concentrations dropped, that was when the Little Ice Age was around. So if you look at the time, like comparing it here to here, where this is the Inter Ice Age time, the period of time, you'll notice that we've been out of an ice age for a very long period of time. So if they peaked by now, surely, because they never go above this level, do they? They've peaked here. So that means they should be starting to go down. This ice age over here, okay, there was fairly warm there, but they've peaked and they should start going down. So we should be heading for a new ice age. So you should be wondering what the ice age that started at the end of the medieval warm period is. Ever since temperatures dropped down to the Little Ice Age, you're wondering why it hasn't continued. So yeah, we'll cover that next week. We're just going to give you these words to let you think about. The Industrial Revolution and global warming. And with that in mind, think about these words until next week when I release the third and final part of my global warming lecture. So yeah, I hope you liked this video. Please do give it a like. Please do share my videos. Please do comment on what you think of them, and please subscribe to my channel so you can see more of this content. Please do ring the bell so you can keep up to date when I release the final part of my global warming will end the world lecture. And please do comment on if there's any other topics you want me to cover, give lectures about, anything. Until next week, just keep these keywords in your mind, and I'll explain why in next week's episode. See you next video, comrades. Until then.